Good morning, students. Welcome to the online classes on the second chapter, electrostatic potential and capacitance in physics for standard 12th. Today I would begin with the last figure which I have discussed in the last class, wherein I discussed the potential energy for a pair of charges, or in general a system of charges placed in external electric field. Suppose there are two charges q1 and q2 placed at 2 points whose position vectors are r1 vector and r2 vector. At these 2 points, suppose due to the electric field present already, that is external electric field, because of that suppose the potentials are Vr1 at this point and Vr2 at this point. Then the total potential energy, if you remember, we had discussed, it had three terms. The first term was due to the potential energy due to these two charges, that was given as 1 by 4 pi epsilon naught times product of the charges q1 q2 by separation between them. The other two terms were due to the external field, were due to the presence of these charges in external potential or field, and was given as q1 multiplied by potential at that point, that is Vr1 vector, plus third term was q2 multiplied by potential at that point, that is Vr2 vector. So this was the total potential energy. Based on this, there is a question on the screen. I would like to discuss that question. So please see that question carefully. The first part of the question, bit A, it says you have to find the electrostatic potential energy, which I am writing as capital U, for a pair of two charges, one 7 microcoulomb, other one minus 2 microcoulomb. And it is given that there is no external electric field. Only these two charges are present. And their locations are given minus 9 cm 0, 0, plus 9 cm 0, 0. It is clear that these two locations are on x-axis. Suppose this is origin, so minus 900 will be at 9 cm to the left of origin, and plus 900, this one, will be to the right of origin. So this is 9 cm, this is 9 cm. So this total distance from this point to this point will be how much? 18 cm. It is this distance between these two charges which we need. And at these two locations, it is given in the question there are two charges. One is q1, q1 value is suppose 7 microcoulomb, and other one is minus 2 microcoulomb, and the separation between them becomes 18 centimeter, which we can write as 0.18 meters. So first part of the question is to find electrostatic potential energy. So how do you find electrostatic potential energy? So electrostatic potential energy U is nothing but 1 by 4 pi epsilon naught into q1 into q2 upon separation between them. Now it is given there is no external field, so there will be only one term. Now you know this value, you know the values of q1 and q2. Microcoulomb means, micro means you have to multiply by 10 to the power minus 6, or you can convert in meters. This will give you the answer. Now q1 is positive, q2 is negative, so you will get negative answer. This you can calculate yourself, students. This answer you will get as 0.7 joules. This is the example from your prescribed textbook, that is NCERT, that is example 2.5. Let's see second part of this question, part B. What does that read? You have to find the total work done by an external agent to separate these two charges q1 and q2 to infinite separation. So you hold these two charges q1 and q2 and then increase their separation to infinity. For doing so, you have to do some work. How much work is to be done by you? That is being asked. You know, students, work done by the external agent we have denoted by the symbol W external, and that W external is nothing but equal to change in potential energy. This is nothing but final potential energy minus initial potential energy. Final potential energy is the potential energy of these two charges at infinite separation. So this is U infinity I can write. And initially they were separated by separation R. So I will use this symbol U infinity minus UR. Now at infinite separation, you know, potential energy is taken as 0. So the answer becomes minus of UR. UR is minus 0.7 joules. So this is our UR. So the answer becomes how much? Plus 0.7 joules. So this much amount of energy you have to spend, this much amount of work you have to do in separating these charges. Now for part C, I'll rub this part. So the first part, its answer is minus 0.7 joule, and for second part it is 0.7 joule. Third part is important, students. See this question, what it is asked. Here it says you have to find the electrostatic potential energy for the same pair of charges, but this time there is an external electric field that is given as E is equal to A times 1 by R square, where A is some constant whose value is given. Already you had one term that was minus 0.7 joule. Now you have two more terms there will be, and those terms will be due to the external electric field. Let's see how do we calculate that. So for part C, the total potential energy U will be having three terms as we have discussed earlier. One term which we have already calculated is this one. Apart from this, Q1 will multiply with potential at its location, and there will be one more term, Q2 into potential at its location. The first term we have already calculated, students. So this factor is how much? That is minus 0.7 joules. Now we know what are the values of Q1 and Q2. So Q1 and Q2 are 7 microcoulomb minus 2 microcoulomb, and R1 and R2 are the distance of these charges from origin, that is 9 centimeter and 9 centimeter. Note that I am asking about distance. Distance of this point from origin is 9 centimeter only. See, this is our x-axis, this is origin, this is 1.900, this is other point minus 900. This distance, if I ask, you will say 9 centimeter. This distance also, if I will ask, you will say 9 centimeter only. Here we have Q1, which is 7 microcoulomb, and here we have Q2, which is minus 2 microcoulomb. The positive charge is placed at minus 9 centimeter, so Q1 is positive and Q2 is negative. Now we have to find what are the values of VR1 and VR2. Only then we will be able to calculate this potential energy. What is given? It is given that the value of electric field varies like so, A by R square, where R, you should remember, students, R is the distance from origin. If you know electric field, can you find potential at a point? We have already discussed the relationship between electric field and potential. So potential at a point we have defined as negative integral E dot dr from initial to final point. So here we take the reference point as infinity, final point as R. Please check your notes which we have done earlier. Potential at some point is defined by this particular relation. So this becomes minus integration E vector will write as how much? A by R square. I am writing its magnitude. Now this electric field suggests, you know, for a point charge the value is 1 by 4 pi epsilon naught Q by R square. It is in that form. So electric field will be directed radially outward for a positive charge and inward for a negative charge. So if there is some charge over here placed at the origin, electric field direction will be like so. So E and dr will take in same direction. So it becomes E into dr. Now what is dr? dr is a very small displacement in the direction of increasing R. So A is constant, it will come out. What will be left? Integration of dr upon minus R square. This integration you can solve it out. You will get A times 1 by R. And the limits are from where to where? Infinity to R. if the limits are from infinity to r, then we'll get 1 by r minus 1 by infinity. 1 by infinity is 0, so we'll get the answer as a by r. So this is the value of potential. So Vr is equal to a by r. Now I'll use this particular formula. So U will become equal to, first term we have already calculated, minus 0.7 in SI system, plus second term Q1. What is our Q1? Q1 is 7 microcoulomb. 7 microcoulomb means 7 into 10 to the power minus 6 into VR1. VR1 will be A by R1, where R1 is the distance of this charge from origin. What is this distance? 9 centimeter. That means 9 into 10 to the power minus 2 meters. Is it clear, students? Then is any other term left? Yes, there is one more term, plus Q2. How much is our Q2? Q2 is negative 1, that is minus 2 microcoulomb. So minus 2 into 10 to the power minus 6 coulomb multiplied by VR2. What is potential at R2? Potential at R2 will be A upon R2. But what is R2? R2 is the distance of that charge from origin. So this distance is also how much? That is also 9 centimeter. So I'll write it as 9 multiplied by 10 to the power minus 2 in SI system meters. Now this value of A is already given in the question. Put all these values and do the calculations. You will get the answer in SI systems, that is joules. I hope this method is clear, students. So the first and second parts were easy. Third part, from the given electric field, first you should calculate the value of potential, and then you should use the concept for finding the potential energy for some system of charges present in external potential or external field. Okay, let us proceed further. The next topic that I would like to discuss is to find an expression for the potential energy of an electric dipole placed in external uniform electric field. This electric field, we will take it as uniform. Here as shown, there is a dipole placed. P vector is the electric dipole moment. You know P vector, it is a vector whose magnitude is q times 2a and is directed along P cap, where P cap is unit vector directed from minus q to plus q. So here theta is the angle between P vector and E vector. These lines are the electric field lines. It is uniform electric field. This is P vector. Students, we have already discussed earlier, when a dipole is placed in external electric field, the field exerts some forces on the charges. So this force will be q times E. This force is also q times E but in opposite direction. These two forces are equal in magnitude, opposite in direction, and that produces a torque on the dipole. That torque is given as P vector cross E vector. So its magnitude is how much? P times E times sine of angle between the dipole moment vector and the electric field vector. So we have tau is equal to Pe sine theta. The path that we will discuss over here for finding potential energy is that if this dipole is rotated through an angle d theta, how much work will the external agent do, or how much work will the electric field do, and from work we will find the expression for potential energy. So this is the torque due to electric field. So I will write it is tau electrical. Its value I am writing. So external torque needed to keep the dipole at equilibrium will be tau external, and its value will also be how much? Pe sine theta. Remember, these are actually vector quantities. If one of them I write as plus, other one of them I must write it as minus. Their signs are opposite, but I am not putting vector sign here, so I am not putting the plus and minus signs. So external torque will be same value, will have same value, but its sense will be opposite. So electrical torque, if it tries to turn this dipole in clockwise sense like this, the external torque will electrical torque will turn it clockwise, external torque will be needed in anti-clockwise sense. If both of them are applied, it will be at equilibrium. Now suppose the orientation of dipole is changed. Orientation means the angle which it is making, from theta to theta plus d theta. Now when I say theta plus d theta, it can't be in this direction. See, this is the direction that makes angle theta with the electric field. So theta plus something means I have to go like this. This direction corresponds to theta is equal to 0. This is theta is equal to 0. This is theta is equal to something, say theta. Then theta plus d theta will be like this. If this dipole turns like this, now see, the electrical torque is trying to rotate the dipole clockwise, but d theta angle is in anti-clockwise sense. Therefore, during this small angular displacement, the small work done by electrical fields is dW electrical. How will you find the work done? Work done, what is the formula? So in case of rotation, we will apply the formula torque times d theta. How much is torque due to electrical field? We are finding the work done by electrical field. So tau is P times E times sin theta, and this is d theta, and we must put a negative sign, because we know if torque and the angular displacement are in opposite direction, work done will be negative. So torque is in this direction, clockwise sense, and d theta is in opposite sense. So therefore, total work done in changing the orientation from some initial angle, say theta I, to some final angle, say theta f, we will find the total work done. So this total work done by whom? Total work done by electric field in changing the orientation of dipole from theta I to theta f, that I will write as WEL. So total work done will be integration of this factor minus P E sin theta d theta from theta I to theta f. Now minus P and E are constants, so we can take them out. Integration of sin theta is minus cos theta, and then we have the limits from theta I to theta f. Now this minus and this minus we can cancel. So therefore W electrical becomes how much? It becomes P times E times cos of theta f minus cos of theta I. Now this is our electrical work done by the electric field. By definition, we know the change in potential energy, change in electrostatic potential energy, which we will write as delta U. How do we define that? Change in electrostatic potential energy is nothing but negative of work done by electrical forces. See, WEL we have got this much. If you wish, you can write in terms of W external. This was tau external, likewise you can find W external. W external will be just negative of this, minus PE cos theta f minus cos theta I. It should be like this. And in that case, we will write delta U is equal to positive of W external. So in some books you will find definition in terms of this. In some books you will find while derivation they have found W external. In some books you will find W electrical. I will prefer this one. So now how do we write this expression then? Delta U is the change in potential energy. So change in potential energy is nothing but final potential energy minus initial potential energy. Final means at theta f, initial means at theta I. So this is equal to negative of W electrical. W electrical we have got this much. It's negative. So it becomes how much? Minus P times E times cos theta f minus cos theta I. So this is the expression for change in electrostatic potential energy for an electric dipole placed in external electric field. If you turn the dipole from angle theta I to theta f, its potential energy will change by this much amount. So I can write it like this also, minus Pe cos theta f minus Pe cos theta I. Now we'll choose a convention, and that convention is a bit unique. That convention says the potential energy of electric dipole at a particular, see, angle theta can take what values? It can take the values from 0 to 2 pi, that is 0 to 360 degree. Out of these orientations, one of them we have to choose as a reference. Reference means where we can assume the potential energy to be 0. That angle is chosen as pi by 2. At this particular angle, theta is equal to pi by 2 means when the dipole is placed perpendicular to the electric field lines, that particular orientation has 0 potential energy. It is just a matter of choice. It can be taken as 1 also. By convention, we choose this value of potential energy to be 0. If this is so, then if the orientation of the dipole changes from initial value theta to, initial will take 0, pi by 2, theta is equal to pi by 2, to some final value that is theta, then this expression now we can write in an alternate form. So we will set theta I and theta f values to be pi by 2 and theta. Instead of theta I will write pi by 2, and instead of theta f I will write theta in this particular expression. So what will we get? U theta f. Theta f means theta minus u theta I means pi by 2 is equal to minus p times e times cos of theta f. Theta f means theta minus cos of theta I means pi by 2. Now in this expression, students, it is clear that this particular term is 0 by convention, and cos 90 is also 0. So what is left behind? The left behind things are this, that potential energy of electric dipole which makes an angle theta with electric field lines is equal to minus P times E times cos theta, and this can be written as minus P vector dot E vector. So this is the derivation for potential energy for an electric dipole placed in external electric field. Please practice this particular derivation. So there are two derivations. Last chapter we have done the derivation for torque. Torque is equal to P cross E, and here we have discussed potential energy for a dipole, that is given as minus P vector dot E vector. Next, in this context, I would like to discuss the equilibrium. If you remember, students, equilibrium of dipole in external uniform electric field we have discussed earlier also, but today we will revise that again, keeping into consideration both the torque values and the potential energy values. See, we have discussed two things. First, torque is given by the formula P times E times sin theta, and potential energy today we have discussed, that is given as minus P dot E, that means minus PE cos theta. Knowing these values of torque and potential energy, we can discuss about the equilibrium of a dipole. A dipole is said to be in equilibrium. That means net force is always 0. This electric field, if you take it as uniform, net force, there is no doubt, is always 0. So net force is 0, no problem in that, because one force is towards right, other force is towards left, if electric field is towards right, and their magnitudes are equal if the electric field is uniform. So net force is 0, no doubt. Then for equilibrium we should also have net torque to be 0, but torque is given by the formula P times E times sin theta. So net torque, it will be 0 if this factor, that is sin theta, is 0. And when will sin theta be 0? Sin theta will be 0 when theta is either 0 degree or 180 degrees. Now these are the two possibilities of theta for which the torque will be 0. If theta is equal to 0 degree, then that particular equilibrium, see, both these angles correspond to equilibrium, but theta is equal to 0 degree corresponds to stable equilibrium, and theta is 180 degree corresponds to unstable equilibrium. So for stable equilibrium, what is the torque? Torque is P times E times sin 0, that is 0. For unstable equilibrium, what is the torque? That is also P times E times sin 180, that is 0. What is potential energy here? Potential energy is minus P times E times cos of 0 degree. Now what is cos 0? Cos 0 is 1. So this becomes minus PE. Now what is potential energy in unstable equilibrium? That is minus P times E times cos of 180 degree. What is cos 180 degree? Minus 1. So that minus and that minus becomes plus, and we are left with P times E. So potential energy in case of unstable equilibrium is plus PE. Now what is the meaning of stable equilibrium and what is the meaning of unstable equilibrium? See, in the context of mechanics students, let me try to explain you. Suppose you have a hilltop like so. There is a hill top and there is a valley. If we put a ball somewhere here, which I'll call as position A, and somewhere here, which I'll call as position B, then the normal reaction offered by the hill or the ground and the gravity will balance at both these positions. So both these positions A as well as B correspond to equilibrium. This is also equilibrium, this is also equilibrium, because the net force might be 0 in both these cases. But this particular equilibrium is stable equilibrium. What is the meaning of stable equilibrium? It means that if this ball be shifted slightly towards one of the directions, then it will oscillate like so, and after some time it will come back to its original position as expected. However, if this ball be shifted even slightly, do you think it will come back? No, it will roll down the hill and will occupy some other position, but not its initial position. That's why it is considered as unstable equilibrium, whereas this equilibrium is one that is stable equilibrium. So stable equilibrium means the dipole, if it is displaced from its stable position, from its equilibrium position, if it is able to come back to its initial position, then it will be called as stable equilibrium. And from this particular orientation, if it is displaced slightly, we will find it will never be able to come back to its original state. That's why that equilibrium is called as unstable equilibrium. For example, you see theta is equal to 0 degree means the dipole will be placed like this, minus q, and this one will be plus q. So this is the direction of dipole moment. Theta is equal to 0 means P vector and E vector are parallel to each other. Now suppose it is slightly displaced from its equilibrium position like so. Then this becomes minus q and this becomes plus q. On plus q there will be force QE in this direction, in the direction of electric field, and on minus q there will be force QE opposite to the direction of electric field. These two forces, don't you think it will apply a torque? Yes. And what will be the direction of that torque? That torque will try to bring this dipole. See, this is the dipole. One force here, one force here. So this will try to bring the dipole back to the initial equilibrium state. That's why this theta is equal to 0 degree. That angle is corresponding to stable equilibrium. Let's see what happens in this case. If theta is equal to 180 degree, that means the dipole has dipole moment vector oppositely directed to the electric field. Electric field is towards right in this figure. Here it is minus q2 plus q. Let's see what happens if we turn the dipole. Suppose it is turned slightly like so. Here we will have minus q, here we will have plus q. Now you see, on plus q the force will be in the direction of electric field, on minus q the force will be opposite to the direction of electric field. These two forces, do you think, will bring the dipole back to its initial configuration like so? No. What will happen? This will continue. If you move the dipole like this slightly, it will turn completely like so and will start oscillating like this, and if there is some friction, it will stop at this particular orientation only. What is this for orientation? Stable equilibrium, theta is equal to 0 degree. So if the dipole is initially like this, where I am pointing in the direction of p vector, then if you displace it slightly, the torque will act so as to increase this angle, and then the dipole will start oscillating like this and will stop at this particular orientation. So this is the meaning of stable and unstable equilibrium of a dipole. In both the cases, you should remember what is the value of torque, what is the value of u. Okay? And one more thing you can understand, students, the value of u is less in case of stable equilibrium. More is the stability, lesser is the energy. You see, u is equal to minus p into e, and here u is plus p into e. So this is more, this is less. So the potential energy should be less in case of stable equilibrium. The lesser is the energy, the more will be the stability. Okay students, I'll stop here. In the next class we shall take up electrostatics of conductors. So see you in the next class. Thank you.